All right, so this is the question that motivates us. And I think the stakes are high here. Many approaches to understanding the bulk, the thermofield double eternal black hole correspondence, Ryu Takiyanagi, geometry from entanglement, tensor networks, ER equals EPR, code subspaces for bulk reconstruction. All of these suggest that any complete bulk description of quantum gravity, if there is such a thing, must be able to describe these states. Well, in this talk we'll use a very simple diagnostic of the discrete spectrum that flows from finite entropy. We'll look at the long-time behavior of some bulk correlation function, where O is some simple operator corresponding to an observer hovering outside the horizon of a black hole. Written in boundary variables, you have inserting a complete set of states, you have some matrix elements squared, and some oscillating phases. At early times, this thing decays exponentially, quasi-normal mode behavior. But at late times, these phases in the chaotic discrete spectrum cause this thing to oscillate in an erratic way. It becomes exponentially small and no longer decreases. Well, to focus on these oscillating phases that do the dirty work, let's just get rid of these matrix elements, which are slowly varying. And so we consider a related quantity, just with the oscillating phases and some Boltzmann weights to tame the high energy spectrum. You can see that this thing is the product of two partition functions with beta shifted to plus IT and beta shifted to minus IT. We'll call this thing ZZ star of T. In quantum chaos, this quantity has been used for a long time. It's called the spectral form factor. It's basically the Fourier transform of the energy differences in the theory. Here are some properties that we'll need. At time 0, this is just the square of a partition function. If we work at infinite temperature, beta equals 0, and we have a system with a finite number of states, L, then this is just L squared, which is e to the 2s. If we assume the levels are discrete, which you expect in finite entropy, and non-degenerate, then at long times, these phases cancel out if you do a little bit of time averaging, or J averaging in SYK. And so only the m equals n term in this sum matters. And so in fact, z of beta squared goes to z of 2 beta, which is just L, or e to the s. So this function, as you go from short to long time, goes from e to the 2s to e to the s, an exponential change in size. And one of the questions we'll want to understand is how it makes this transition and what it tells us about the dynamics of the theory. Well, SYK can serve as a toy model to address these questions. Douglas's talk gives a lot of the background for this, but I'll just review a couple of the salient points. SYK has a sector dual to ADS2 dilaton gravity. It's chaotic and has a discrete spectrum at finite n. And especially, it has this nice description in terms of G and sigma that, well, these are really a master field kind of description, but they have some aspects that are reminiscent of a bulk description. These are ON singlet fields. They're non-local, which you might need to project into the bulk. And there's a non-perturbatively well-defined description for this quantity ZZ star. You have two copies of the theory, two replicas, so that means that G and sigma each carry two indices, A and B, that run from 1 to 2. And these integrals over 4, really 3 copies of G and sigma with a well-defined action provides, if you do a contour deformation, a completely well-defined, non-perturbative description of the theory. So in practice, what this means is any funny business we find on the left-hand side has to be duplicated by the G sigma integral, and how he does it is an interesting question. It's a question I'm not going to have a lot to say about today, but it is an interesting question. In addition, this theory has a finite dimensional Hilbert space. The dimension is 2 to the n over 2. We'll call that L. And so it's amenable to numerics. And these have proven very valuable in giving us guidance about what to look for. Unfortunately, we're not yet in the situation of doing experiments in quantum gravity, so it's nice to be able to do computer experiments on toy models of quantum gravity. And that's some of what I'll talk about. A large group of us got together and decided to look at the model to answer some of these questions. Even with first initials of last names, this is a long author list, as you can see. Well, here are some results. This is this quantity ZZ star on a log-log plot. Is this a pointer? Can you see this pointer? Yeah, I guess more or less. So this is a Z of normalized, so ZZ star at time 0 is 1. This is log of time and log of magnitude. At late time, you can see the magnitude is exponentially less, here by a factor of over 1,000. This is this constant time average value. And we see that at early time, we have a feature we call the slope that is essentially a consequence of semi-classical quantum gravity. But at later time, we have a ramp feature and a plateau that we'll see are consequences of the random matrix behavior of this system. Between them, we have a feature we call the dip that we now believe is just a crossover. When this gravity signal gets small enough, it reveals this random matrix structure. The slope is determined by semi-classical quantum gravity and is non-universal. It depends on what kind of black hole you're looking at. In SYK, the slope goes like 1 over t cubed. That's just the Fourier transform of this one-loop Schwarzian result that the density of states vanishes like a square root. Douglas described this. In BTZ, Dyer and Gurgurari analyzed this model by summing over all modular transforms of the BTZ saddle, or more generally by modular transforms of conformal blocks, and found a rapidly decreasing feature, but then modulated by exponentially small oscillations, that when you translate it corresponds to exponentially small ripples in the density of states. So 2 different black holes, 2 different short-time behaviors. But we expect that at long time, this gravitational signal will fade away, and you'll be left with this universal random matrix behavior that is a characteristic of quantum chaotic systems. Well, ZZ star is essentially the Fourier transform of the pair correlation function of eigenvalues. Given an eigenvalue at E, what's the probability of having one at E prime? It's a basic result of random matrix theory that this correlation function is given by the sign kernel expression. The Fourier transform of this expression just looks like this, a ramp and a plateau, and that's what this feature represents. You can understand now this funny part of this plot that it decreases before coming to its asymptotic value. It's just due to this minus sign. The energy eigenvalues are not uncorrelated, as they are in this feature, but they're anti-correlated. They don't like to be close to each other. Eigenvalues repel. There's what's called spectral rigidity, and that's the source of this dip. We conjecture that this pattern is universal for quantum black holes. There's some kind of non-universal gravitational pattern here, and then when it goes away, the next thing you see is this random matrix behavior. There's a bit of evidence for this in these melonic models. These models at leading order in large N have the same behavior as SYK, but at subleading orders differ. In particular, there's no randomness in the Hamiltonian. There's a bit of numerical evidence from this group that it's very hard to work with this model numerically. All you can look at the state of the art is 30 some odd eigenvalues, unlike the thousands of eigenvalues that go into this picture. But still, you can see a clear indication of eigenvalue repulsion. That's the essence of this random matrix behavior. To do something in super Yang-Mills would be a bit more difficult, and so it's going to be hard to collect a lot of evidence about this. But already, since we know what to shoot for, we can make an interesting observation, or more accurately, raise an interesting question. If this is the thing that we're supposed to get, and if the time is much less than this plateau time, you could ignore this rapidly oscillating sign. You find this decrease quadratically in the energy difference. This is what's called spectral rigidity and gives the ramp. To study random matrices of rank L, you would just do a 't Hooft perturbation theory where the expansion parameter is 1 over the rank, which is 1 over L. And this is just first order in perturbation theory. It's a perturbative result in random matrix theory. But in SYK, L is 2 to the n over 2. So 1 over L squared is e to the minus some constant times n. It's a non-perturbative effect in SYK. We're not sure what it is, but it's going to be that size of effect. But even more puzzling, if we get to the plateau and this rapidly oscillating sign is important, in random matrix theory, you would turn a sign squared, you would analytically continue an energy, and look at an e to the minus L effect. That's a standard instanton in random matrix theory. In this case, it's called the Altshuler-Andreev instanton. And you can derive this effectively in that way. But in SYK, this turns into an e to the minus e to the n effect. So somehow, a non-perturbative definition of the model, like G sigma, has to produce effects like that. That's an interesting question we don't know the answer to, but now we know that we're going to have to look for something as subtle as that in a non-perturbative description of this model. Well, I can give you a status report. We've decided to, I guess the right expression is, to make a tactical retreat. Okay, Phil Sod and I are looking at the Q equals 2 model, this model where you just have random masses for fermions. The behavior of the model is pretty clear, but understanding it in the G sigma language turns out to be quite subtle. I'm confident we'll be able to understand this case, at least, and then with our experience, I hope we'll be able to go back and answer these more subtle questions. Well, I hope to keep you posted on that. But in the remainder of the time, I want to talk about another feature that helps guide us for what to look for, and that's a timescale question. And the question is, at what time does this ramp begin? Well, you might think it's just this dip, but that's really not the case. This is just a crossover when gravity stops hiding the underlying signal. You can see this because these come from two different places. Here's this density of states that Douglas displayed. The edge of this is where the square root singularity occurs. That's responsible for this ramp, for this slope. The ramp is about correlations more in the bulk of the spectrum. And so these are two different phenomena, and they just compete, and this is where they stop, or one wins over the other. The real question is, in some sense, this ramp continues underneath the slope. When does that continued ramp stop? This quantity in condensed matter physics is called the Thouless time. The example that people usually talk about in condensed matter physics is you have a single particle hopping, let's say on a line, with random hopping parameters. The Hamiltonian matrix would then be some kind of banded matrix with random entries. It turns out that the characteristic time there is the time for a particle to diffuse across this line. So it's a time that goes like n squared. At times longer than that, the spectrum looks random matrix-like. At times shorter than that, you get some other behavior characteristic of this diffusive phenomena. Well, what we'd like to do then is examine this question here. We'd like to follow the slope underneath this irritating background that is what semi-classical quantum gravity has become for us. Okay. So what you want to do is you want to somehow eliminate these edges, and so we can impose a Gaussian filter. Instead of studying a partition function with a Boltzmann weight, we can just put a Gaussian weight that lets us look at the center and cuts off the edges very smoothly, so we don't have any sharp edges making power law trouble. So we compute this quantity we call y star, and we try to go under the bottom. Here's the original curve. Let's blow up this region near the dip. This dip time is about 200 time units. This purple line is the dip. It's computed at beta equals 0, so there are these funny wiggles here. But think of this as like this red line, and then this green line. I realize green line is not the right thing to talk about here, but okay. There's this green line that goes underneath the slope all the way to times of order 10. So there's a factor 20 of time where you see a ramp not being hidden by gravity anymore. So we have an onset of a ramp around time equals 10. There's a lot of ramp left underneath here. Notice that in this region, the ramp, even though it's a real effect, it's exponentially subleading in more familiar observables like correlation functions. So it's hard to dig out, even though it's there. Now, as we vary n, this position doesn't change much. It's pretty clear this is an upper bound on this ramp time. You can see this straight line really wants to keep going. We just can't cut out any more of the edge in this model. So the fact that it doesn't vary much suggests that this dependence on n is very weak, even though this is an upper bound. Maybe this thing varies logarithmically with n. Now in this game, as soon as you see a logarithm in n, you say, ah, scrambling. So one possibility is that this timescale is due to scrambling. Well, we've looked into this possibility, and we'll investigate it. And I'll tell you in advance what we think the answer is. We think the timescale might be logarithmic. There's a maybe there. But we think with high confidence that it's not related to scrambling. So I'll lead you through our chain of argument here. The first thing we have to do is stop looking at logarithms. If you're doing numerical experiments, especially where you're limited n, looking for a logarithm is a fool's errand, okay? So one thing we could do is study a different system where we have n geometrically local qubits, that is a nearest neighbor chain of qubits coupled together site I to site I plus 1 with random couplings and sigma x, sigma y, sigma z chosen kind of randomly also. This model is a scrambling model. It's chaotic. It will have random matrix kind of statistics. But the scrambling time will be n, not log n. Things have to propagate all the way along the chain. N is easier to detect than log n. That's what I just said. Further, this model doesn't have a zero temperature entropy. It has a Gaussian density of states, and in fact, the Gaussian is wide enough that in time, in Fourier transform, the slope dies very quickly at a time of order 1 over square root of n. So we're going to get rid of the slope really fast in this model. So here's a picture, I guess, with 15 qubits. There's this slope that dies like a bomb. It's out of the way. At late time, you see a ramp and plateau. This theory has random matrix statistics at fine enough timescales. But in between, there's some kind of other behavior. Maybe it's related to diffusion. We don't really know. So we just made an empirical fit about when the ramp starts without really a theory. This is kind of a guess. And we plotted these times as a function of n. So this would be the ramp time as a function of n. If it were scrambling, this should be linear. And I don't know, I can't really draw a good straight line through this. Well, you can draw a straight line, okay? But it seems like it wants to be quadratic. Maybe it's diffusion. One thing is, if you try to draw a straight line, the times are wrong. To get out to 16 qubits, it takes 200 time units. The Lieb-Robinson velocity here would say you'd get across the system in like 2 or 4 time units. So there's several reasons to believe that scrambling is not going on here. Well, we try to make an incisive argument that scrambling is different than the phenomenon we're seeing. And one way to do this is to realize that scrambling is a very generic phenomenon. It's about the growth of a simple operator, let's say 1 qubit, turning into sums of products of more and more qubits until you cover the entire system. So because it's this architectural phenomenon, it occurs in a lot of contexts, including what's called a Brownian circuit. A Brownian circuit is where you replace time evolution with a single Hamiltonian by a product of different Hamiltonians at each time step. And these Hamiltonians are drawn from some ensemble where, let's say, you vary the j's. So here you'd vary the j's at each time step. It's often useful to think about this in terms of unitary gates, where you build up this unitary as a product of different unitary gates drawn from an ensemble, and you take their product. This is a very useful construct because you can analyze the dynamics of this Brownian system, including scrambling, analytically. And so we could try to look and answer our question analytically. The way you do this, or one way you do this, is you think of the action of these Brownian unitaries on a density matrix in the qubit space. So this is a density matrix made out of bras and kets, each drawn from this qubit Hilbert space. You can rewrite this as strings of products of Pauli matrices, because Pauli matrices take you from a qubit space to a qubit space. And so what we're going to do is we're going to look, this is a technical comment that I'll elide here, I think. So this defines a Markov process as you choose these random unitaries on chains of Pauli matrices. Here's I, that's sigma z, that's sigma x. If you're a quantum information person, that's what they look like. So you have a Markov process on these strings of Pauli matrices. A simple set of random unitaries is to think of random 2-qubit gates. So you imagine dividing this nearest neighbor system into even and odd bonds, and then you go around, you hit the even bonds with a random U4 unitary in the 2-qubit Hilbert space. You hit the even bonds, then you hit the odd bonds, and you repeat. And that defines a Brownian motion on this set of Paulis. Well, the action is simple. If you have a pair of identities in this chain, it goes to a pair of identities because the U and the U dagger cancels out. If you have any other pair of Pauli's, like Ix or Xz. This random unitary, whoops. This random unitary sprays them uniformly over the other 15 possibilities with uniform probability. So this defines this Markov process. II goes to II, AB goes to the other 15 uniformly. And then what you want to do is you want to equilibrate these chains of Pauli's. The initial condition for an out-of-time order correlator or a commutator is to start with one Z at the end of the chain, that's like a simple operator, and ask how long it takes to equilibrate this last qubit here that would give rise to a large commutator between the operators at the two ends of the chain. Well, let's just think about what this Markov process does. If you hit any place in here, you're out of luck. II goes to II. The only place where you can make equilibration happen is by hitting this bond. Zi can get sprayed all over. Then the next step, you can hit number 2 and number 3. That sprays all over. And so you can linearly build up equilibration across this. The equilibration moves like a front across this chain. So the time to randomize this last qubit is of order n. That's the scrambling time of order n. And you can compute the Lieb-Robinson velocity and other things this way. But now we want to look at R quantity. For spectral statistics, we want to imagine building up this unitary as this product of Brownian circuits, and then we want to compute the moments of that unitary. K equals 1, 2, that's like the time in the spectral form factor. Well, what we're looking for is that this thing is given by random matrix statistics, which means it's given by its Haar average. Well, let's look at K equals 2. That's the only one that's easy to look at. Numerically, if K equals 2 gets to its Haar average, all the higher Ks do also. There's an interesting question there that I won't turn to here. And so it turns out the slowest term when K equals 2 is a monomial of this form, where A's are all the same index. There's no unitary invariance until the end, so the different index sums behave in different ways. So this particular monomial you study by taking U and U dagger applied to this projection operator. And you can take the state A, for instance, to be all spins up in the qubit chain. Well, what is the projection onto all spins up? You can write it in terms of Pauli's as I plus Z, tensor product over all the qubits. But now you can expand this out into strings of Pauli's. There's a typical expansion. It's like coin flips. This is easy to equilibrate. There aren't long strings of I's here. It equilibrates in times of order 1. Well, that's not quite right. If you have a string of coin flips that's n long and ask for the longest string of all heads, it's of order log n. So the time to equilibrate is of order log n, which is much shorter than the linear scrambling time in this model. So here's a very clear distinction between scrambling and the equilibration of the spectral form factor. This is closely related to an observation that these authors made about quantities like this and something else called the frame potential. That you can rewrite these things in terms of correlation functions of very complicated operators. And the question is not how a simple operator gets big, that's the scrambling question, but how very complicated operators equilibrate. And we see here it takes a rather short time. But now we have to go back to our numerical data that said for a fixed Hamiltonian, things actually look power law. There's some kind of propagation going on. Diffusion, maybe ballistic, but some kind of propagation. Now, it's a general rule in these systems, if you take a geometrically local system where there's propagation and turn it into a Q-local system where everything talks to everything else, that's like a system in very high dimension, then power laws turn into logarithms. So without knowing the detailed dynamics, it seems like a reasonable guess that if there's propagation here, it should turn into a logarithmic time in something like SYK. So this seems like a plausible guess, and we're trying to put flesh on it, but right now let's make it a plausible guess. This is important. This time scale is important. Because the black hole evaporation time for a small black hole is of order the entropy, which is n here. So if this time scale is shorter than n, a logarithm of n is shorter than n, I'll remind you, it means that this random matrix behavior sets in quite early, even before a black hole has time to evaporate. So even in small evaporating black holes, this signature of the graininess, of the finiteness of the entropy is visible. It's not a long time phenomenon. It's just exponentially damped. So it's still in principle possible to suss out. Well, that's something we've learned. It's something to guide us as we explore this topic. But we still need to know what these phenomena mean in quantum gravity. Well, and we hope to be able to tell you something about that in the not too distant future. Thank you.
Questions? Okay, well, let me start. You had a ramp asked about the onset time for the ramp, which
Yes.
was completely swamped by the slope
Yes.
in the model. So how does one extract sort of the physical meaning from that onset, given that it wasn't sort of visible directly in the model? What is the significance that it's sort of hiding?
I wish I knew. Okay? That's what we'd like to know. Okay? It's got something to do with about the discreteness of the entropy, but we don't have I don't have an answer to that. Otherwise, my talk would have been different. Okay.
Yes, Herbert.
I have a very naive question. At the beginning of the talk, you wrote down, but you then didn't really discuss, a 2x2 version of the action with G and sigma
Yes.
for two replicas.
Yes.
Are saddle points in that extended action relevant to anything you've talked about?
Perhaps. We've looked for saddle points, and we can't find a saddle point that obviously describes what we're looking for. But it's possible that
What property should such a saddle point have? Can you say anything about that?
well, it should when you go study in real time, it should have a linearly increasing contribution to ZZ star to duplicate the ramp. There are some obstructions to a single saddle point describing these phenomena. One is that if you actually look at the sample-to-sample variation of the signal, numerically, the variance is order 1. Where you think of a single saddle point as describing this phenomena, the variance should be suppressed by n. So there's certain indications that a simple saddle point description, a new saddle point, is not enough to describe these phenomena. But it could be a large collection of saddle points or something like that. We don't know, and that's one of the obvious things to look for. But that's along the line you'd like to think about. This e to the n is a little more upsetting in terms of saddle points. And, well, I think that's all I have to say about that, unfortunately.
Is there an understanding from this propagation model for where the e to the n could? I mean, these qubit chains where you...
About where the e to the minus e to the n comes from?
Yeah.
No, absolutely not. No, no, it's when you get to random matrix behavior, something like that must be going on. But this gives no extra evidence for that.
For that. So you see you see a very sharp slope and you see the ramp, but you don't...
But yeah, that will be just a single e to the minus n effect. Okay, but we have no extra insight into what it means in terms of some bulk variables.
And second question, I mean, what tunes this parameter p in these models? Is there an understanding for how you can go from diffusive behavior to increasing the strength of interaction to get it towards a log?
Say the last thing again?
I mean, how do you go in a simple diffusive model where you just have random walk type behavior?
Yes.
You get root n. You don't get n to the p. So
Well, you get n squared, actually.
Sorry, you get n squared. But
Yes.
What gives you other exponents in
Other
what
exponents
kind of
like the random matrix exponent?
Yeah.
Well, there's a rich theory of this, and I'm not sure I can give you a good answer, but you can actually, in something like a banded matrix, you can actually write something like the G sigma variables, and you can actually see the crossover from diffusive to random matrix behavior as a certain set of saddle points comes to dominate. Okay, so this is a rich story due to, well, a number of physicists, especially Russians, Miralin, where you can actually take random banded matrices and study them and see this crossover quite explicitly. The problem is there, the only expansion parameter is L, because you're dealing with random matrices. This interplay of N and L is absent. And this is the new, we're kind of in a second quantized version of these hopping models, and that's the big mystery for us. Okay.
Any other questions? Shiraz.
I may have misunderstood completely. Sorry, but the time scale for you showed a graph which had a dip and then rose again. And the time scale for that dip, did you say, was approximately log of n?
Let's say in this qubit model?
No, in the actual SYK model.
So here? So this green line, where this sets in?
Yes.
Okay. Well, first, to orient you, so the location of this dip is probably exponential in n. This would be e to the n time, and this would be e to the n over 2 time. E to the s time and e to the s over 2 time. Okay, that's what we think they scale in entropy scaling. And then the guess would be that this thing would continue and be a log s time.
Okay, so my question is this. In ADS5 cross S5, if you looked at a 2-point function that was decaying,
Yes.
I thought that the expectation was that the decay would continue until times of order entropy, at which point the new saddle point, namely just pure thermal ADS, would kick in and sort of ameliorate that decay. So I thought that you should see something, at least in that case, at times of order entropy. You don't see anything in your model at times of order entropy?
There's an extra ingredient in correlation functions in that you have this extra envelope caused by the matrix elements that gives you an exponential decay. Part of that difference is we've stripped off the matrix elements, and so this early time behavior looks different than a correlation function. We think the universal stuff will be the same, essentially because the matrix elements, by eigenstate thermalization, behave smoothly. So there might be a smooth envelope to strip off, but these universal random matrix things will be the same.
Thank you.
And in fact, we were able to see at late times in correlation functions these features. So again, I would think the entropy time is just a crossover time. You got to get rid of this boring, perturbative quasi-normal mode physics. You'll excuse me, Veronica, for that invidious remark. In order to see this non-perturbative exponentially small effect. Okay.
Okay. Let's thank Steve again.